you can make the host. Okay. Okay, so Utsav, what we proved is if X is a Cat-Kappa space, then the unique geodesic joining any 2 points X, Y, this depends continuously on X and Y. Okay. And so what that means is if we have Xn converges to X and Yn converges to Y, then I want to show the geodesics Xn, Yn converge uniformly to the geodesic XY. Okay. So what I do is I consider these three geodesics Xn, Yn, Xn, Y, and XY, right? So then I reparameterize them to be defined on the interval 0, 1. Okay. And then I look at the point, say, gamma n of t here, dividing this geodesic in the ratio t is to 1 minus t. And then I look at alpha n of t here, dividing the ratio t is to 1 minus t. And then I look at gamma of t, dividing this in the ratio t is to 1 minus t. And so then by the previous lemma, the distance between here and here, gamma n t and alpha n t, this is less than the distance at the end, which is y and y. And similarly, if I go backwards from y towards xn and y towards x, then the distance between alpha n t and gamma t is less than or equal to the distance between xn and x. And so therefore, by the triangle inequality, the distance between gamma n t and gamma t, this is less than or equal to the distance gamma n t alpha n t plus alpha n t gamma t. So that's less than distance y and y plus distance x and y. Sorry, x and x, this should be x and x. X and x. So this goes to 0 as n tends to infinity. So therefore, gamma n converges to gamma uniformly. Is this okay, Utsav?
Yes, sir. Yes.
Okay. So as a corollary, what we get is that any cat-kappa space is contractible. And the proof is very simple. You just fix a base point, x naught in x, right? And then basically what you do is you, for any point in the space, you have a unique geodesic joining it to the base point. You parameterize it on the interval 0, 1, and then you contract it towards the base point along this geodesic, right? Okay. So you let for P in X, sorry. For P in X, let gamma P from 0, 1 to x be reparameterization of the geodesic x naught P. Okay. So then define your homotopy H from x cross 0, 1 to x P comma T goes to gamma P of T, right? So when T is equal to 1, this is the identity map. And when T is equal to 0, this is the constant x naught. And this is continuous because gamma P depends continuously on P and T, right? Is this clear?
Yes.
Okay, so this is continuous by previous proposition. So this gives a contraction to a constant. Okay. So the space is contractible. Basically, it's a radial contraction, right? I'm just contracting along geodesics to the origin. Okay. Is it clear?
Yes.
See, the point is that the geodesic joining is unique and depends continuously, right? So therefore, you can contract along such geodesics. Okay, so cat minus one, cat kappa spaces are contractible. They have no topology for kappa less than or equal to 0. Okay. In particular, they're simply connected. And now what I want to do is look at a few things. Let me see what's next. So, right. So let me give you an example, which is not a, well, I've given you an example first. So one example is a metric tree. Okay. So what is a metric tree? It means a geodesic metric space where for any geodesic triangle, each side is contained in the union of the other two sides. So that means, for example, basically, you could take, for example, as X to be a simplicial tree. That means a graph without any loops. Okay. This is slightly less general than a metric tree. Graph without loops. Or more generally, X equal to metric tree. Each side in geodesic triangle is contained in the union of the other two. So I mean, here's an example of a tree. You can have this branching tree like this. And maybe this has more branches and this has more branches. Okay, so this is an example of a tree. Is this okay? Yeah. Right?
Yeah.
Now the thing is, what does a geodesic triangle in a tree look like? A geodesic triangle in a tree looks like a tripod, right? A Y shape. Yeah, for example, if I take say this point, and say this point, then what is the triangle? The triangle is basically this geodesic, and this geodesic, right? So that's a Y shape, you see, right? It's isometric to this tripod, right? Yes?
Yes.
Okay. So here each side, this side XY, this is contained in the union of the sides YZ and ZX, right? So that's the definition of a metric tree. It's a geodesic space where each side in a geodesic triangle is contained in the union of the other two. Okay. So this is my geodesic triangle. All right. Now, what happens for the comparison triangle? So if I draw a comparison triangle, so I want to show the cat kappa inequality, right? So if I take 2 points, let's say in the sides xy and xz, so if they belong to this segment which is common to both the two, then the distance here is so, well, it's going to look like this and this, right? So this distance is, say, so if this thing is t and this thing is s, then this distance is t minus s. And then I have to show if this is t and this is s, then right, this distance. So if this is, say, P and Q, then this is P bar and Q bar. And if this is, say, X bar, then distance P bar, Q bar, this is greater than or equal to distance P bar, X bar minus distance Q bar, X bar, right? By the triangle inequality. Yes? So
Yes.
that is T minus S, which is equal to distance PQ. So in this case, the kappa inequality is true. Okay. So this is trivial. This, I'm not using any property of M2 kappa here. But what if I take my points instead are like this, say P is here and Q is here. So then what can I do? So suppose I take a situation like this. X, Y, Z. I take a P here and I take a Q here. Right. So actually, this is not the case. This case is also easy, I think. The case I need to look at is when I mean my
Q.
So P is here. Okay, and say this distance is S and this distance is T. Okay, fine. Actually, let me look at the picture so I don't get confused. I've done the proof here. So, right, the distance between these two is T. So suppose I'm looking from the vertex Q. Okay, so I'm thinking of this as a point along PQ and this as a point along QR. Okay, and I have points X, Y here, and this distance is T. So then let me look at the comparison triangle. So then what I do is I take the comparison points, right, from Q bar. Oh, I'm looking from P. So yeah, okay. So this distance from P bar to X bar is the same as P to X, and the distance from P bar to Y bar is the same as P to Y. Okay. And what I do is, if this distance is T here, I look at this distance T in this triangle here, and I move back, right? So then what happens is, if I look at this point here, then this point and X bar, these two are equidistant from P bar, right? Yes. So if I call the distance between X bar and Y bar, I call it S, then what do I get? I get a picture in H2 where basically this is P bar, this is X bar, this distance is the same as this distance of this point, right, from P bar, right? This distance and this distance are the same. So these two lie on a circle around P bar, right? These two lie on a circle around P bar. And then I'm looking at the circle of radius T around Y bar, right? So these two circles meet at this point, and then you can see in H2, these two circles don't meet at any other point, right? Yes. So this point X bar, this is outside the circle of radius T here. So that means this distance S is greater than or equal to T. Is this clear?
Yes.
Yes, so that will tell me that distance X bar Y bar is greater than or equal to distance XY, right? So that is the cat kappa inequality. Is this okay?
Sir, we are not dealing with the case when Y bar is on the geodesic Q bar R bar, right?
Right. Yeah, okay. So if Y bar is here, right?
Yes.
So then I have to look from Q bar. Okay.
Sir, can you please extend the comparison triangle one?
Sorry?
Can you please explain this triangle that you are getting from this triangle in the graph?
This is the comparison triangle, right? This is the comparison triangle in M2 kappa. And then in this comparison triangle, I'm looking at the triangle P bar, X bar, Y bar, right? So that's this triangle. So here, basically, if I move backwards by an amount T, where T is the distance from Y to X, if I move backwards by this amount T, then I get 2 points which are equidistant from P bar, right? So they lie on a circle centered around P bar in H2, right? So that's a Euclidean circle in the disk, okay? And this point also lies on a circle of radius T around Y bar, right? So that means X bar, it lies on this circle, which is tangent to this circle at this point. So it's going to lie outside this circle, right? So this distance from X bar to Y bar will be greater than this distance from Y bar to this point, which is T. So therefore, and T is equal to the distance from X to Y. So the distance X bar, Y bar is greater than or equal to the distance XY, right?
Yes.
So maybe the case I'm not covering is this case. is this case precisely, right? Yeah, where I look at them like this, viewed from X. Okay, so let me try and do this. I didn't think about this. So if this is X bar, Y bar, Z bar, this is Q bar, and this is P bar. This is the case, Orkojit, right? You're saying?
Yes, sir. Yes, this is the.
Okay, so let me call this distance, say, what should I call it? Lambda, and let me call this distance mu, right? So then I move back lambda and mu here, right?
Yes, yes.
I do this. So I get these 2 points like this. And then so the distance between QP is lambda mu. And I want to say the distance between Q bar, P bar is lambda plus mu here. And I want to say it's greater than or equal to, right? So, oh, these 2 points are equidistant, right? These 2 points are equidistant. These 2 points are equidistant. Right.
Equidistance from Y.
From X bar. Equidistant from X bar, right? So if this, I call this distance, say L. So then this is L and this is L. So these two lie on a circle around X bar. And now I have to show that if I move by lambda and I move by mu, then the distance is at least lambda plus mu. Oh, why is that true? In fact, the distance, that doesn't seem to be true actually. That doesn't seem to be true. This is not a good picture. Wait.
Sir,
Yes.
sir, we can use that angle property, right?
Right. Yeah, but this.
I know the proof is by the angle property.
That's true, but this
Comparison.
should also be true, right? This picture should also work, right?
Yes.
But it doesn't look like it works. This distance from Q bar to P bar, it looks smaller than lambda plus mu, right? If it's a very thin triangle. Oh no, this geodesic has to dip in. I see. Okay. So maybe I have to use the hyperbolic law of cosine. So if this is theta, so what do I have? So basically, So actually this will be in the hyperbolic plane. These will be multiplied by some 1 over square root minus kappa. So let me call that a constant, say, I don't know, C or something. So C. So in H2, this would be CL, CL, C lambda, C mu, right? And so then what do I have? I have, if this distance is C times the distance D, so then I have cos H of CD is equal to cos H of yeah, I'll have to think about this. This should
Sir.
follow from hyperbolic law of cosine.
Sir,
Yes.
I think we can do it this way. We join X bar to P bar, then try to show
X bar to P bar, right? This along this geodesic, right? Let me think about this. I think, I mean, as Orkojit is saying, there's a way using angles, but I think you can do it by direct computation. It should be possible.
So Y bar, distance between Y bar and P bar is lesser equal, is greater or equal to distance between Y and P, right?
Right, because Y and P is, this distance is the same as this distance, and then plus this distance.
Triangle inequality for this hyperbolic triangle and then.
No, not quite, not quite. We don't exactly have that. So. Actually, it's enough. Let me forget about this constant C. And okay, I'll think about this. Let me avoid this for now and just carry on. We're almost out of time, so I just want to do 1 or 2 more things. I'll think about this. Yeah, so, okay, fine. So here's something which is useful. Maybe I'll do this later. Any local geodesic is a geodesic. So local geodesic means a curve such that for any T naught in the interval I, gamma is a geodesic in a neighborhood of T naught. So I don't need this right now. Let me skip this for now. I might come back to this later. And also convexity of balls, I don't also need really right now. So let me skip this. Balls in a cat -1 space are convex. In a cat kappa space are convex. So, acha. Okay, yeah, let me do this bit about angles. Angles, this is useful. So, okay. All right. So, suppose XD is a geodesic space. So if I take 2 geodesics, C1 and C2, which have the same starting point. So C1 0 is the same as C2 of 0. then the Alexandrov or the upper angle between CC prime is the angle CC ACC prime in the interval 0 pi defined by AC1. Oh, I'm writing C. My notation is all bad. Okay, I'll just do it here. Fine. So, okay. So definition. So, so X is a geodesic metric space. And if C and C prime from 0A to X are geodesics such that C0 is C prime 0, then the Alexandrov angle A of CC prime is defined to be the limb sup as T prime tend to 0 of let me call it so let me call this equal to this starting point P. The angle at P 0 between CT C prime T prime. So what is this angle where this angle P0 QR, this denotes the comparison angle. The angle in the comparison triangle denotes angle in the comparison triangle delta bar P bar Q bar R bar in R2 so the angle at P bar in the comparison triangle delta bar P bar Q bar R bar in R2. Okay. So basically what this is I have a point P and I have two geodesics C1 and C and C prime, and I look at points close to P. So this is C of T and this is C prime of T prime, where T prime are small. I look at this triangle PCT C prime T prime, and then I form a comparison triangle in R2 P bar CT bar C prime T prime bar. Okay, this is delta bar in R2. And I look at this angle theta in this triangle in R2. Theta is what I'm calling this comparison angle angle 0p ct c prime t prime. Okay, and then I take the limb sup over theta as t and t prime tend to 0. Is it clear, the definition? Yes. Yes, are you there?
Yes, sir.
Is the definition clear of the Alexandrov angle? So I look at these small triangles. I look at the corresponding comparison triangles in R2. I look at the angle at P bar, and then I take the limb sup of this angle as T and T prime tend to 0. Is it all right?
Yes.
Okay. So this gives me a notion of angle between geodesics in a metric space by using comparison triangles in R2. All right. By using comparison triangles in R2. Now, it turns out that this is, in fact, I can do the same by looking at comparison triangles in M2 kappa. If I look at the limb sup of angles in M2 kappa, and it turns out that I would get the same answer, but that is actually not so easy to prove. I've written something here, but this proof is incomplete. So this is not, this is non-trivial, actually, that if I, instead of R2, if I used M2 kappa, I would get the same limb sup. I would get the same limb sup. It's a bit delicate, the proof, so I'm not doing it. So what I want to finish with is this last lemma, that if I have 3 geodesic paths starting from a point P, so say C, C prime and C double prime, then the angle function, the Alexandrov angle, satisfies a sort of triangle inequality. The Alexandrov angle between C and C double prime is less than or equal to the Alexandrov angle between C, C prime and between C prime, C double prime. Okay. So we've got less than a minute. Let me stop this meeting. I'll start a meeting just to finish the proof of this. It's not very long. It'll just take 5-10 minutes. So let me stop this and we'll come back in another.